Hello, my name is Paima Ahmadipour. I'm a PhD student in Shawnee Lab at USC. My project is about developing an efficient algorithm for learning of low-dimensional latent dynamics in multi-scale spiking and field potential population activity. Modeling spike and field potentials together is useful for studying the underlying population dynamics and improving performance of brain-machine interfaces. Our previous multi-scale dynamical modeling framework is based on an expectation maximization algorithm, which is an iterative algorithm, thus computationally expensive. However, in some applications, such as tracking adaptation in basic science studies or real-time learning in brain-machine interfaces, a desirable feature for a learning algorithm is computational efficiency. Here, we develop a more efficient multi-scale dynamical learning algorithm based on subspace identification, abbreviated as SID, and validated in simulations and real data. The traditional subspace identification algorithm is used for identification of a linear state space model with continuous observations. Therefore, it's suitable for modeling continuous valued field potentials. We can empirically compute the future past covariance of field potentials and estimate the model parameters using the traditional SID. While extensions of SID have also been developed, they are still only for single-scale neural data, such as discrete spike counts or continuous field potentials. A critical question that remains to be answered is how to extend SID to learn a multi-scale latent dynamical model for both spiking and field potentials together. The discrete spike counts can be added to the model as a Poisson distributed values with latent firing rate. That is a linear function of the same latent brain state. Extending SID to multi-scale modeling has challenges because first, log firing rates are latent. Therefore, computing covariance of log firing rates and field potentials, which is needed for the SID algorithm, is challenging. Second, the covariance-based SID methods cannot guarantee identification of valid noise statistics. Enforcing valid statistics is also challenging. Third, field potentials and the spikes have different time scales. For example, we may observe spikes at every time step while observing LFP power features every m time steps. Therefore, spikes give information about dynamics of A, while the LFP power features give information about dynamics of A to the power of m. Accounting for different time scales in identification using SID is another challenge. In this project, we developed an efficient multi-scale dynamical learning algorithm based on subspace system identification by solving the aforementioned challenges. Our algorithm uses empirically computable covariances of field potentials and spikes and extracts all the model parameters of our multi-scale model with latent states. Next, we validate our algorithm using numerical simulations. In simulations, we investigated the parameter identification error of multi-scale SID and found that SID accurately identifies the model parameters. You can see that the identification error of all the parameters decreases as the training sample size is increased. Also, all the errors converge to less than 2% at the last training sample size shown on the plots. Next, we investigated how adding scales of neural activity to each other changes accuracy of learning of the dynamical modes. Here, dynamical modes are the eigenvalues of the state transition matrix A in our model. First, we added gradually LFP channels to a fixed number of spike channels and found that the performance is improved due to addition of information from LFPs to spikes. Additionally, we found that the improvement due to addition of LFP channels was larger in the low information regime. In other words, when we had a smaller number of spike channels. Furthermore, we found consistent results when adding gradually spike channels to a fixed number of LFP channels. This showed that the performance improvement was bidirectional and not due to the dominance of one scale of neural activity to the other one. After that, we compared performance of multiscale SID and multiscale EM. To do so, we looked at different iterations of EM and compared the performance of converged EM with that of SID. We found that SID is more accurate than the converged EM in identification of dynamical modes. We also compared the computation time of converged EM with that of SID and found that SID is much faster than EM. Next, we validate our multiscale SID algorithm using a non-human primate multiscale neural dataset during a random target reaching task from Sebi's lab. We compared performance of multiscale SID and multiscale EM. To do so, we looked at different iterations of EM and compared performance of converged EM with that of SID. We found that SID is more accurate than the converged EM in predicting LFP and spiking activity across all latent state dimensions. In addition, we compared the computation time of converged EM with that of SID and found that SID is much faster than EM across all latent state dimensions. Finally, we compared performance of multiscale EM and multiscale SID at latent state dimensions corresponding to the best neural prediction accuracy of each of the models. We again found that multiscale SID is faster and more accurate in predicting the neural activity compared to the multiscale EM. In summary, we have developed a multiscale dynamical learning algorithm based on subspace system identification that can model discrete spike counts and continuous field potentials together and model neural signals with different time scales. Also, we validated our algorithm using numerical simulations and an NHP dataset and showed that multiscale SID outperforms multiscale EM in computation time, accuracy of identification of dynamical modes, and prediction of neural activity. Further, multiscale SID outperforms single-scale SID due to addition of information across scales. Finally, in the future, we can develop an adaptive version of our more efficient multiscale dynamical learning algorithm to study plasticity and for real-time learning in brain-machine interfaces. Finally, I would like to thank my advisor, Mariam Shanechi, and all members of our lab and the funding sources. Thank you for your attention.